I believe the slides are visible. Okay, good. So we're going to start off with RISC V Basics. As soon as you enter the RISC V world, you will find a lot of news articles and different open source cores, and there's going to be a lot of terminology and jargon that's going to be thrown around where it's assumed that you know what those mean, right? So we're going to talk about a few basics so that helps you sync up with all things that that is a common vocabulary that is used in the RISC V world of such, right? So the standard naming convention to describe the standard extension supported by an implementation, right? So RISC V is a collection of different extensions. And in order to say that I have a RISC V processor with X, Y, Z features, there is a way to specify that, right? So you start with a string called RV. RV stands for RISC V. By the way, so the 5 is Roman number 5. Does anyone know why it's 5? Any reason why it's called RISC V and not RISC 4, 3, 2, 1, or 6 for that matter?
Due to five-stage
I'm just
pipeline?
guessing, is it because 5-stage pipeline?
No, it's not.
It is the 5th version of RISC ISA.
Yes, that's exactly that. So RISC basically came out from Berkeley. The RISC processors, the very first was David Patterson and Christie and their teams were working on the Berkeley Architecture Research Lab. So they were the ones who've done multiple iterations on a minimal RISC-based ISA. So there was RISC 1, RISC 2, RISC 3, RISC 4. RISC 5 is when they had stabilized and they had a very clean slate implementation of the instruction set. That's why it's called 5. Remember, ISA is just an instruction set architecture. It does not govern what the microarchitecture is. The number of stages in a pipeline is microarchitecture. Whether you have caches, branch predictors, out-of-order cores, superscalar cores, all of that is microarchitecture. An instruction set like RISC V does not mandate anything on the microarchitecture. You can have the same instruction set, but the processor could be an out-of-order multi-core, multi-threaded system, or it could be as tiny as a 2-stage core running a bare metal, a real-time operating system on it, right? So V, they use the Roman number V, the Roman number 5, which also indicates vector. One of the founders of RISC V, Christie Asanovic, the professor at Berkeley, he is a veteran in vector architectures. His thesis is one of the most exemplary works that have been done in vector processors. And if any of you are interested, I think that's the starting point to start looking at what and why we should be doing vectors today. So his fascination with vectors is why they also kept the alphabet V, right? So that's about RISC V. So when you start saying that, I have a RISC V core and what does it include? You start by saying it's an RV core. RV stands for RISC V. After that, you have a number which can either be 32, 64, or 128. Right? So this defines the width of the integer register file and the size of the user address space, right? So today people say, oh, I have a 64-bit processor, I have a 32-bit processor. What does that mean? That basically says that your register width or your data compute elements, maximum load store operations that you can perform or can be 32 or 64 bits wide, right? So typically the integer or the data type that you can define in your software stack is going to be 32 or 64, depending on the number that you define here. So RV32 or RV64 is how we define them. The next alphabet is going to be I and E. I or E. I stands for integer ISA. E stands for embedded ISA. They're pretty much the same, except that in the E subset, you only have access to 16 registers instead of 32 registers. Right? So they've just shrunk down the number of accessible registers. And then the final one, which is the XXX that you see here. Maybe I should enable my pointer. Yeah. So the XXX is a series of alphabets. and where each alphabet or each character over there is going to indicate the subset of extensions that are currently supported. Right? So we look at these alphabets later. And remember, RISC-V is a collection of different instruction sets. It's extremely modular. The minimum amount of instructions that you need to support is just 40 instructions. With that, you can actually boot 40 plus, let's say 10 more, 50 instructions. You can actually boot an entire operating system along with it, right? So each extension is versioned. You have a major and a minor 2.1. So your integer extension can be at 2.1. Your floating point extension can be at 1.9, and so on, right? And the example at the bottom, basically RV32I 2.1, M 2.0, A 2.1, basically indicates what version of each extension have you implemented. Couple of more basics. In the RISC-V ISA or any processor that implements a RISC-V, the RISC-V instruction set, it is supposed to have at least 32 integer registers, right? X0 is always hardwired to 0. RV32E, as I mentioned, has only 16 registers. Instead of 32, it has access only to the upper 16 registers, 0 to X15. Whereas the RV32I or RV64I, they all have access to the entire 32 register set. If you are implementing floating and single or double precision floating point extensions, you need to maintain a different register file of 32 registers. Now the width of the register is defined by the ISA. So as I said, if you say RV64, then each of these integer registers is 64 bits wide. If you say RV32, each of those instructions become 32 bits wide. Now apart from the unprivileged, you also have access to privilege modes. There are 4 privilege modes, as Professor mentioned. There's machine, hypervisor, supervisor, and user. Machine is the highest, or it's like the root mode, where it has access to the entire system. And user mode is the lowest privilege. It's like your applications or web browsers that you're building. It has the least amount of access. It needs to get permissions either from the supervisor or directly from the root user to make certain environment calls or some machine mode related operations. And finally, we also include a couple of CSRs in the RISC-V spec. These are known as control and status registers. These are part of the privilege spec. We will look at a few of them when we talk about the machine mode today. They basically help maintain the context and the different attributes and aspects of the current state of the code. Right? So apart from the 32 registers, you can have a significant number of control and status registers, which will help maintain the context of the architecture. So any questions so far? Okay, so maybe I'll ask you guys a question. So why do you, what do you think would be the reason of having a separate register file for floating point operations? Right? So for integer, we have 32 registers, and we are saying that if I have support for floating point single or double precision support, I need to maintain a separate register file of 32 registers, which is where all the floating point numbers will be stored. Why do you think that is?
We 64-bit for each registers.
Sorry?
In case of floating point, the 32 extra registers, each register would be of 64-bit against 32-bit of integer, right? Because we require more values.
You can assume a RV64I, in which case all the 32 registers are 64 bits wide, the integer registers, and your double and your floating point registers are also 64 bit wide. Now, why do you need a separate register file in that case?
Because we may use a floating point unit.
Okay, but so the floating point unit can still have, it can still read registers from the integer register file, right? Floating point unit is a compute unit, right? You provide inputs, it will compute, give you the output. The inputs come from the register file and the outputs are written back to the register file. Why do you need a separate register file if you could have used the same integer register file for storing the floating points? Anyone else?
separating complexity of floating point from integers process. Integers data.
So complexity where?
In processing instruction of floating point.
Actually, the normal registers are used for for a process switching. The normal registers are also used to store the addresses and all, but these floating point registers, they are specifically used to compute for mathematical instructions.
Correct.
So for
So
that
if
purpose,
you actually do end up, let's say we just had one register file which is storing both integers and floating points, right? What would happen there is your integer registers are also going to be used for your AVI operations and stack maintenance and thread pointers, global pointers. You're soon going to run out of registers, and especially when you now overload the same registers to hold floating point also, you get access to even less number of registers, right? So from the compiler's perspective, in order to enhance or to maintain performance, so that all the function calls and everything is properly done, the number of argument registers, callee function registers, and all of them, you don't want to overload them with or superimpose multiple functionalities in them. So you maintain a separate register file, which will hold only the floating point registers. The integers will be used to basically carry out all the ABI related functions flawlessly, right? So the compiler has more register resources. It does not undergo register spilling if you have separate register files. If you have the same register file, then you'll end up doing a lot of transfers between memory and registers so that the compiler can continuously use registers for its purpose, right? But having said that, register files are costly. They don't come cheap. So there is a new extension that is being proposed in RISC V. It's called the ZFINX, right? Basically, the idea is you perform floating point from the X registers, right? Now, this is useful in embedded spaces where you are really area constrained. You're not looking at performance, but you want floating point for maybe some necessary calculations, which are not really performance oriented, but you are very sensitive about the area that you give to your chip. In which case, it makes sense to use the same registers as the integer registers to store floating point also. Okay, good. Now this is a current status slide of RISC V. It's going to give you all the pointers of where you can go and identify the spec and different things that are happening. Always visit riscv.org. That's the main website. All news, all latest developments, what's happening, what's not, it's all present at riscv.org. These specs are available as the RISC V ISA manual. I think the link is a little old, but it should redirect you to the actual GitHub space. Apart from the privileged and the unprivileged spec, the RISC V community has also worked on some of the uncore related specifications like debug, trace. These are all optional specifications. You can have your own debug implementation, or you can follow this debug spec also, right? Any one of those. But these are things that the RISC V community has grown to see that a lot of people are interested, and therefore it's created a spec so that there can be uniformity and there can be reuse of code and tools and utilities across different vendors, and it can be vendor agnostic in some sense. So on the right, you are basically seeing a lot of these alphabets under the extension name, right at the bottom. You have the M, which is ratified A, F, D, C. So M stands for multiplication and divide instruction set. It has around 10 instructions there. You have the A, which stands for atomics. If you are doing operating systems, or if you want to boot Linux, or if you have multi-core systems, you will need support for atomic operations. These are the ones that perform read, modify, write operations on the memory. F stands for single precision floating point support. D stands for double precision floating point support. Q is quad precision, 128-bit precision floating point. C is compressed. Compressed is basically all the other instructions above M, A, F, D, Q, C, Q, the instructions in them are all 32 bits wide. Whereas in compressed, you have a subset of instructions which can be represented as 16 bits, right? All of these 16-bit instructions are equivalent to have a direct mapping to one of the 32-bit instructions, right? These are not new instructions that you're presenting in compressed, but it's just a shrunk down version of some of the existing 32-bit instructions which are already present. Can anyone guess why do we have a compressed extension? Why this helps?
For embedded systems?
Correct, but how? What does it help embedded systems with by having compressed?
So for hardware constrained environments of like the SoC boards with less specifications or low processing.
I understand that, but I'm asking exactly where in your solution will adding compressed give you benefit? Let's say you have sorry?
Lesser bandwidth. The buses will be reduced, so the chip size will reduce and everything will shrink down.
Okay.
Less power use.
Less power, not really.
Okay.
But yeah, less power. That's going to be a long shot to say that it's going to be less power. The power savings are not much. In fact, I believe the power savings are increased when you have a compressed support. I'll explain that. But anyone else? So when I reduce a 32-bit instruction, which is 4 bytes, into a compressed instruction, which is only 2 bytes, the immediate...
It makes the decode much simpler.
No, it makes the decoder a little more complex. Every time you add a new extension, the decoder needs to decode it, right? So now we are adding compressed. You're saying that, oh, now I'm going to give you 16-bit instructions also, which you have to decode. So one of the immediate aspects or the most eminent benefit of shrinking a 32-bit instruction to a 16-bit instruction is memory size, right? To store the same program, to store the same hello world, I will now require less amounts of bytes in the memory. So if I had 32-bit program, which took 256 kilobytes of, let's say, RAM, maybe with compressed, I might need only 150 kilobytes or 170 kilobytes or 128 kilobytes. I don't know. If you're lucky enough, everything shrinks by half and you go down to 128. Usually not the case, but if majority of your instructions do shrink down, your memory density increases in the sense you're able to pack in more instructions for the processor to execute in less amount of space. This obviously increases the cache. If you have a cache, which means you're storing more instructions within the cache, right? If you had each line, let's say, was 32 bytes of a cache line, which means it can store approximately eight instructions. You could now have the ability to store 16 compressed instructions. Right? So your cache hits will increase, your performance will also increase, but I believe power and area will also increase because you will have to decode the compressed instructions separately. And you'll have to know additionally, not separately, but additionally you'll have to decode them as well. And the fetched logic for the cache becomes now a little more tricky because as soon as you give compressed support, there are instructions. A 32-bit instruction can start at a 2-byte boundary or a 4-byte boundary. So whenever you get a chunk of data from the instruction cache, you don't know whether it's a 16-bit instruction or a 32-bit instruction. And depending on that, you need to increase the program counter. So to support compressed, you add a little bit of extra logic in the fetch stage of your pipeline in order to ensure correct functioning. Right. So that's where compressed is. But yeah, I think purely from the embedded space and reducing memory density reducing memory footprint, compressed adds a lot of value. And then you have counters, LB, JT. So you can go to the RISC V specification, go through all of them. These are all in draft. Some of them have been ratified just 3 weeks back. I don't know if you've been following RISC V, but 15 new subset of extensions have been ratified just before New Year's. And that's going to add a lot of boost to the community. I think RISC V is going to start entering compute domains where the ARM or some of the other processors have they hold monopoly there. I think ARM is soon going to find its way and consume market share there also. Okay, so we'll now quickly go through the base ISA spec. This is the RV32I extension. This is the minimum extension that you have to implement. If you're a RISC V core and a 32-bit RISC V core, this is a compulsory extension. Everything else in the spec is not compulsory, it's all optional. You can choose to implement it, you can choose to not implement it. But if you want to call your processor a RISC V core, you have to implement a 32-bit RISC V core, you have to implement the RV32I. If you're a 64-bit processor, you need to implement the RV64I, right? So architectural state typically defines what is the user visible data storage elements that that is accessible, right? So as a software user, the one who's writing the program, what do I have access to? So we have access to 32 registers, of which the 0th register, that is X0, is hardwired to 0. Okay. All the other 31 registers are general purpose. We do not assign any special functionality to any of the registers. The stack pointer, thread pointer, they can all be part of your software. The specification does not mandate any particular functionality to any registers. Right? There is a separate ABI spec which you can refer to, which is what the software community uses in order to maintain cross binary compilations and stuff like that. So that they do have an application binary interface which assigns that, okay, we will always use X2 as a stack pointer, X1 as a return address, X3 as a thread pointer, and so on. But you can always choose to define that and still be RISC V compatible. So for a 32-bit core, we have X length as 32. X length tells you the size of the integer X. Typically in RISC V, X would stand for integer. F stands for floating point. So whenever you look at X length, that's the first variable here, X length equal to 32, X len. That basically indicates what is the integer length size, right? And for right now, it's 32 for us. I length at the end is basically your 32-bit instruction length. So all instructions in the RV32I are going to be 32 bits only, right? We are not looking at compressed today. So quick features, it has 40 base instructions. It's very similar to earlier RISC processors, but without the branch delay slots. Can anyone tell me what a branch delay slot is?
When we encounter a branch, there's basically one instruction which is independent of the branch. We can execute in such a manner.
Where is that instruction?
Like we can put an instruction before branch, immediately after it. It's just an idea.
Yeah, so branch delay slots are basic instructions following the branch instruction. So it is meant for 5-stage pipelines, right? So typically a branch resolution happens much later in the pipeline. It's not at the first stage. It's typically in the decode or the execute stage. So while that branch instruction has reached the decode, or let's say it's getting resolved in the execute stage, right? It's reached the execute stage. You've already fetched 2 more instructions in the pipeline. Right? There's one instruction in the decode and there's one instruction in the fetch unit also. Now, if the branch is taken, then you need to throw these out, right? The 2 spurious fetches that you've done, you need to dump them out. So what people thought was, since I've already fetched it, since I've already decoded it, I will let them execute. And they call them as branch delay slots, right? So they said that even though I'm going to take this branch, the 2 instructions are following the branch will also be executed. Now, this creates an issue in modern architectures because you got to keep tag when you're doing out of order cores or you're doing superscalar cores. It becomes very difficult to pinpoint which set of instructions are part of the delay slot and which need to be preserved and which need not be preserved and all of that, right? So in RISC V, we do not support any branch delay slots. It's restricted to a minimal set to provide reasonable platform for compilers, assemblers, linkers, and operating systems. So 40 instructions are more than enough for you to actually boot a real-time operating system, and a few additional atomic extensions will allow you to boot Linux as well. The equivalent of this number of 40 in ARM is around, I think, 300 to 400. PowerPC is around 275 to 300 instructions. So those are the minimum number of instructions in those specs that you need to implement to be called ISA compatible, whereas here it's only going to be 40. So I have one more question to the audience. We've talked about X0 is always hardwired to 0. Why is that? What purpose or what benefit do you get by doing that?
We can use add instruction to do move operations or XOR instructions to do NOT operations, like increasing the instruction density.
Okay. What else? So 0 is one of the most common constants that you would find in any application today. You either want to zero out memories or your integer initialization start with 0, and move operations, as was previously mentioned. For all of these reasons, 0 is a very important number, and every time to initialize or to use the value 0, if I have to go to memory and come back, it's going to be a little difficult, right? And if I have a register which is always hardwired to 0, I don't need to store those zeros in memory also, right? So it has multiple benefits: initialization of constants, initialization of memories. If you are, certain data structures, you want to do perform move operations, you want to create no ops for that matter. The register value 0 adds a lot of value there. Any questions so far? Okay, so quickly moving on. So this was the standard calling convention or the ABI convention, which is an optional spec. But if you follow this, a lot of the open source software community's work can be reused in your work. A lot of libraries for Linux or everything follow this convention. So if you build your own application, if you follow this, you will seamlessly integrate with other third-party RISC V ABI compatible codes as well. Base instruction format. Now, in RISC V, it's a base ISA. We've mentioned that there are going to be 32-bit instructions, and there are 4 types of instructions, right? On top, you have the R-type instructions. These are register type instructions. So here you're going to have RD. Let me see. Okay, good. So the first one is the R-type instructions. It's a 2-register instruction. You have RS1 and then you have RS2. You operate on them and the result is written into RD. The next is the I-type. I-type stands for the immediate type. RD is the destination register. RS1 is the first operand. And instead of the second operand being RS2, you have an immediate number or a field which is present in the instruction itself. Right? This is a 12-bit constant, which is encoded within the instruction. You extend it, sign extend or zero extend it, compute it with RS1, and you write the result into RD. The S-type is a store type instruction. You don't have any destination registers, but what you have is RS1 and RS2, where RS1 acts as the base memory address. RS2 acts as the data that needs to be written to memory. Additionally, you also have the immediate field, which will tell you the offset of the index relative to the base of RS1. Right? So we'll look into more examples of this, but this is basically a one type of instruction, one type of category of instructions called the S-type. The U type, which is the upper immediate type, basically has a 20-bit immediate field. So if you want to declare really large constants, right, you can use some of these instructions where you can use 20-bit immediate fields to initialize the register RD with. Okay. So depending on this slide, can you make any interesting observations?
There are 64 instructions only.
Sorry?
Are there only 64 opcodes? Because opcode field is set from 0 to 6. So it has 7 bits for opcode.
So these are called major opcodes. Within each major opcode, so if you look at the R type, for example, right? Let's say you've given a category of instructions as opcode 000, just for example. You have the function 3, which is 3 bits, and you have function 7, which is 7 bits, right? So 7 plus 3, 10. So within one value of opcode, you have 1,000 different instructions that you can define using func3 and func7, right?
Okay.
All of which are going to be R type. Now, if I change the major opcode again, and if I define them again as R type, so within R type, I can have significant number of instructions. That's the idea, right? You use func3 and func7 to further distinguish between instructions. So the add instruction could have a func3 value of 0, and a sub instruction could have a func3 value of 1, and all the other bit fields are the same.
Okay.
So one of the interesting observations that you would see is RS1, RS2, and RD are always at the same place. If they exist in a particular type, then they always exist at the same place, right? So if RD is present in RI and U type, it's always bits 11:7. If RS1 is present, it's always bits 19:15. If RS2, it's always 34:20. In places it doesn't exist, you don't matter, but wherever it does, it's always at the same place. How does this help?
Even before decoding the opcode, you can go to the source and destination.
Correct. So as I mentioned, right, register files are are not easy to come. You do have to pay a price for it in silicon and performance and everything. So the register file, you need to provide the operand values, right? The operand indexes, RS1 and RS2 to the register file, or when you're doing a write back, you need to know those addresses. So especially when you're doing operand fetch, you want to access those, you want to put these indexes as soon as possible into the register file. You don't want much of gate delays there. So now that RS1 and RS2 is always at the same place, you can simply take these bits without any computation, without any combinational logic, just feed these 5 bits into the register file directly. So this reduces the critical path before the register files, right? So this has been consciously done. Even new extensions and instructions that are being proposed today, they still follow this follow this criteria that RS1, RS2, and RD, if they exist, they should always be at the same location so that the decoder complexity is not increased. So they've taken huge amounts of care in creating a decoding scheme or an encoding scheme, which is hardware friendly of sorts. The second observation is that the all immediates are sign extended. Now, the good thing about that is if you look at the sign extension, so does anyone know what a sign extension is? Sorry?
Yes, sir. Like if it has one at the MSB, then we continue the one.
Correct. So you duplicate the MSB bit for the upper bits, right? So if I have a 12-bit immediate and I want to sign extend it to 32 bits, then the upper 20 bits are the same as the MSB bit, right? This sign extension is also costly because you have to identify which bit and how many times you want to replicate in hardware. If you look at all the immediate fields, the MSB bit of that immediate field is always bit 31. So irrespective of the instructions, you can quickly build the upper 20-bit field or the upper bits just by blindly looking at 31 and replicating it. Right? You don't have to decode the major opcode and func3 and blah, blah, blah in order to build that immediate field. Because all immediates are considered sign extended, and the sign is always present in bit 31 for I type, S type, and U type. Any questions? Okay. So we're going to add a couple of more instruction types. They're the B type and the J type. So if you look at the B type, it stands for the branch type. It's very similar to the S type, right? It's exactly the same, except that if you look at the immediate fields, the 12-bit immediate in S type was very simple. You have the lower 5 bits here and the upper 7 bits here, right? Whereas in B type, it's a little confusing as to why they've done this, right? You have the 11th bit of the immediate here, then you have 4:1 bits here, then you have 10:5, and suddenly the MSB bit here, right? Similarly, J type is very similar to the U type. Again, the immediate field is all jumbled. Can anyone guess why this jumble exists? Why can't we? Why couldn't we have just used the same thing? Also, remember in the branch type, the immediate bit does not have the 0th bit, which means that the 0th bit is an implicit 0. You're basically defining a 13-bit immediate in a 12-bit space. Right? You assume that the 0th bit is 0, so you always start from the first, second bit 1, and then you populate it. Right? But we could have done 5:1 here, and then we could have done 12:6 here, right? Even that would
To be able to reuse most of the space. For example, 5 to 11 is already defined in S, and 1 to 4 is already there in S. You already have hardware for that. So you essentially are only switching 11 and 12 will be the sign bit here as well. So 11, you're just putting it in front.
Yeah.
That's the only thing which is going to happen.
You want to maximize the overlap of the fields across that, right? So if you look at these bits 11:7, right? For the S type, you have immediate the 5 bits here. If I put this as 5:0 or 5:1 here, none of the bits will overlap, right? The 7th bit in S type is going to indicate bit 0, but the 7th bit in B type is going to indicate bit 1. So my decoding further increases. For every bit, I now have multiple places to look at. But if I do this jumbled scheme, which looks jumbled, but it is not, it ensures that I have maximum overlap. So all immediate bit 4 for S type and B type is the same 11th bit of the instruction. Bit 3 is bit 10 for both. And it's only the 11th bit and the 12th bit which are going to have slightly extra decode logic. But majority of the other bits overlap with each other. The same goes for U type and J type. So this is a quick representation of what we just discussed. If you look at building the immediate field 0 to 31, and you look at what instruction bits contribute to which immediate field. So in the I type instructions, the 0th bit can come from instruction 20. For the S type, it comes from bit 7, and for all the other types, it's 0. Right? So you need a 3:1 mux to decode the 0th bit of the immediate. Similarly, if you look at bits 4:1, there are again 3 options. It's either 24:21, 11:8, 0 or 0. 3 options. So again, a 3:1 mux for each of them. So similarly, if you go on, you will find a maximum of 3 or 4:1 mux to decode any particular bit. And if you didn't have the scheme, you would have ended up with more number of muxes for some of these fields. Is that clear? Any confusions, any questions?
Sir, I have a question. So
Yeah.
If we are trying to have maximum overlap, then why are we placing the 11th bit in the 7th position. We could have just placed, instead of 12, we could have placed 11, and then we'd have a maximum overlap of 11 to 5. Right? Yeah. For the B type.
Yeah. So B type, there is a constraint that you want all the MSBs of the immediate to be presented with bit 31, because that's going to be the sign bit.
Right. Got it.
So you need to place 12 here. And if you placed 11 is to 6 here, then none of these would have overlapped. All the 5 bits would have had a mux on them. So instead, you only create an extra mux for bit 12 and bit 11. All the other bits remain the same. So this is the opcode map. The 6-bit major opcodes that you saw earlier, right? This particular field. The table that I'm going to present now is going to dictate what is the interpretation of those fields, right? So for 32-bit instructions, the lower 2 bits are always 1, 1. Bits 1 and 0 are always assumed to be set. So if those 2 bits are 1, 1, then you know it's a 32-bit instruction. If they're not 1, 1, then it's probably a compressed instruction. Or, yeah, if it's not 1, 1, it's probably a compressed instruction. So today, we're not talking about compressed instructions. We are only going to talk about the opcode, the 32-bit instructions. So here, as you can see, the different values of 4:2 and 6:5. You can have load operations, you can have floating point, multiply, add operations, branches, direct jumps, atomic operations, U-type instructions in AUI, PC, LUI, all of these things. If you have a 64-bit core, then you can also support some of the 32-bit instructions as well. Apart from these, you will find custom 0, custom 1, custom 2, and custom 3. These are reserved spaces that the RISC V has allocated and said that these opcodes can be used by an implementer or by a vendor to define their own set of instructions. Right? If I want to create an AI accelerator, or if I want to create a security accelerator or a safety critical accelerator, and if I want to define new instructions, I can define them using these 4 opcodes, because these are guaranteed to never overlap with the specification ever, right? The foundation will never define these opcodes with a valid new instruction. They can never do that. These have been reserved for customization only. Now, the fields that are called reserved, you can find 3 of them here. These are reserved by the foundation for their own future use. So when they define new instructions later as part of the standard specification, they can choose to use these as per their own free will as part of the specification. This is going to be defined by the RISC V Foundation itself. That's why they're called as reserved. And if you want to introduce new instructions, you should never use the reserved opcode space for that. Okay. So we're going to quickly do, in the interest of time, we're going to quickly go through some of the instructions, the 40 instructions that we talked about. So these are the I-type instructions. Very simple, very straightforward. There's no major funda in this. You have an add I. SLTI is basically set less than. You compare RS1 with the immediate value. If RS1 is less than the immediate value, you set a value of 1 in the RD, in the destination register, or you write a value 0. SLTIU is the same, except that the comparison is going to be unsigned comparison. You then have XOR-I, OR-I, AND-I. These are all logical operations. At the bottom 3 are the shift left, shift right, logical, and shift right arithmetic. Can anyone tell me the difference between shift right logical and right arithmetic? Why do we have 2 different types of shift rights?
One is for the sign preservation and other is for normal.
Correct. So Signed arithmetic is when you're shifting right, or let's say we talk about right logical first. When you're shifting right, you insert 0 at the MSBs. Right, so this is sort of an unsigned shift right. Right, you're simply inserting zeros. In shift right arithmetic, while you're shifting right, the MSB is duplicated with the previous sign bit. The sign bit is replicated always. So this is useful when you want to scale down negative numbers. If you want -8 to become -4, you can use an SRAI, right? But if you do an SRL on -4, -8, it may not be a -4, right? You'll end up with some other number. So we'll see examples over there. So there are 9 such instructions. The semantics are very straightforward. You have an operand, you have an operation which is defined by func3. Right? So for the same major opcode, which is 00100, and remember the lower two bits are all 11, just by looking at the different func3 fields, you're able to distinguish between different instructions. And within the shift left, the immediate field is only 5 bits. Why is it 5 and not 12? For the shift left and the shift right operations, the immediate field is reduced to only 5 bits. Whereas for all the others, it's 12 bits. Can anyone guess why this is only 5?
Because the maximum shift possible is only 32, so beyond that is going to make it 0.
Right. So your integer size is 32 bits. If your shift amount is more than 32, no matter what the value, you'll end up with zeros all over, or you'll end up with all ones, right? If you're doing a shift right arithmetic for that matter. So, which is why we don't need more than 5 bits to indicate the shift size. And therefore, between the shift rights, we are using these MSB bits, 30th bit to indicate the difference between them. Which means now there is more space for the same values of 001, 101, and for the func3 value of 001 and 101, there are, so 2 power 7 is 128 minus 2, 126 more instructions that I can still add by keeping the same value of func3 and opcode, which is still available, right, for the foundation to add new instructions to. So this is a quick example of interpretations of the instructions and how C code gets replicated. For example, translated to assembly. For example, you have f is equal to g minus 10, right? So this in C program would basically, in assembly, would turn out to be an add-I operation where x4 holds the value of g, minus 10 is encoded as a 12-bit immediate within the instruction, and x3 is the variable f. So similarly, if you want to do a move operation, for example, you want to copy the value of g into f, you simply add an immediate value of 0 to x4, which will get written to x3. If you wanted to take a negation of a number, you can XOR it with -1. Right? So remember, though the field is only 12 bits wide, you are sign extending it, which means all the upper bits will also become 1s. And therefore, when you XOR x4 with all 1s, it becomes a negate operation. This is an example of set less than. So let's say f and g are unsigned numbers. If f less than 10, then g is equal to 1, else g is equal to 0. This is your C code. This would translate to a single assembly instruction as this, where x3 and 10, x3 holds the value f, 10 is the immediate value, and x4 will become g depending on the value of f. And if you want to do signed operation, you use SLT. Right? That's the only difference. So this is an example of the difference between how SLTIU and SLTI operate. For example, what you're doing here is you're initializing x3 with the value 0x700. Okay. Now, if you have an immediate value of 0x900, right, which you want to compare with 700 hex, the sign extension of this value is this number, FFFFF900. Now, if I check x3, yeah. Yeah, right. So x3, which is 0x700, and if I compare it as an unsigned number, if I treat this FFFF900 as an unsigned number, definitely this is larger than 700, right? So I set a value of 1 in x5. But if I treat this as an signed number, then this represents the value minus 2048, which is lower than x3, right? In which case we set a value 0. So that's how, for both cases, the sign extension remains the same, but depending on U or the absence of U, the comparisons will become signed or unsigned, and therefore the results will change. Any questions? Okay. So shift operations, very simple. You assume x12 is this value. If I shift left, it becomes 8. If I shift right, it becomes 0. And if I shift right arithmetic also, it becomes 0. But if you assume x12 to be minus 25, this is the value of x12. If I do a shift right logical, I will end up with this weird number of unsigned value. But if I do a shift right arithmetic, the MSB bits are preserved. It's going to push in 2 ones. Therefore, you will get the value minus 7. So 25 by 4 will end up with minus 27. That's the idea of scaling signed integers. The next set is going to be add R-type instructions. These are exactly the same that you found. You have the same set of equivalent operations here: shift right logical, shift left. All of those exist. Except instead of the immediate field, you now have the second operand coming from the register file RS2. Right? And again, here we use punc3 to distinguish between them. And within the shifts, the 30th bit is what is used to indicate the shift right versus shift left. Oh, sorry, shift right arithmetic versus shift right logical. Right, so the operations are exactly the same, except that the operands, instead of being immediate, will now come from register file RS2. Any questions? Okay. So this is a very basic example of compute operations and arithmetic operations. If you want to do B plus C plus D minus E, you're going to have temporary registers like X1, where you'll store the temporary value of the previous operation, and finally X1 gets the value of A is equal to temp minus E, where temp was temp plus D, which was again B plus C, and so on. So in order to check for overflows, we don't have an overflow flag in RISC V, right? So if you're performing add operations and you see an overflow, there is no mechanism that the user can detect it without. I mean, there's no flags, there's no control and status registers that the user can go and probe and check, right? So in order to check for overflows, you will have to use a combination of arithmetic followed by a branch instruction. So for example, if I wanted to do an unsigned addition, and in which case, if I want to check for overflow, I simply check if T0 is less than T1, then it's an overflow, right? If it's a signed addition, I do similar stuff. if I have registers instead and not immediate fields, you need a little more number of instructions, and then you have a branch instruction. So basically the idea is you're going to have an if-else condition somewhere which says that if you do this, then handle overflow separately. In typical other ISAs, you have an overflow flag, which when set, a trap or an exception to happen. Right, so that's why you don't have that. You will have to use the branch operations in order to jump. So if you're not speaking, I would request you guys to mute. Mr. Raju, can you please mute? I can mute you for him. Yeah. Okay. Now we've talked about register files. How do you load and install? How do you populate those registers? Right. You have an architectural state of 32 registers, each 32 bits wide. How do you fill those registers up? One way is to use immediate operations that we saw. You can encode some of those constants in the immediate field and use a series of those operations to create, populate the entire register. But you can also do them from memory. So if you have access to RAM or some other memory, you can copy those data from the memory to the registers or vice versa, right? And in order to do that, you have load and store operations. So the first one we're going to see is the load operation. All of them follow the I-type format. RS1 is the base address. The immediate field is a sign extended index. And RD is where you're going to write the register with the loaded value. So a load operation reads from memory and writes to a particular register. So there are 4 different types of loads. You have an LB, which will do a load byte. What it does is it reads 8 bits of value from the memory, sign extends it, and writes it into RD. Remember, a byte will update the entire field of the RD register. It is not that only the lower bits of the RD are populated. And RD will sign extend the 8th bit to 32 bits and write the entire 32 bits into RD. The same goes for LH, but here H stands for half word. So the size of memory operation is going to be 16 bits. Sorry. LW, which is load word, is going to be 32 bits. Now you're going to have LBU, which means load byte unsigned. You don't sign extend the 8th bit. You just fill the upper 24 bits as zeros. And then you write it into RD. The same goes for LHU. Now for the store operations, we have 3 additional store operations. Those are store bytes, store half word, and store word. Here again, RS1 acts as the base address and the immediate field acts as a sign extended index. You don't have any RD because remember, store operation reads from the register file and writes to memory. There is no update in the register file itself required for a store operation. So in this case, what we will be doing is RS2 will hold the value that needs to be written. What is the register that needs to be copied to the memory? Right? That's what RS2 will hold. So now there is a possibility of something called misaligned exceptions when you perform memory, right? So RISC V is a very, it is the base ISA. If you were looking for a very minimal implementation, you would expect all half word operations, all 16-bit operations to start at a 16-bit boundary. If you want to perform an LH operation, the addresses have to be multiples of 2 always. So address 0, 2, 4, 6, 8, those are all aligned. If I try to do a load half word at an address which is odd, right? If I want to load half word from byte 1, your code should give you a misaligned exception, which means the address is not aligned to the data size that is being requested. Similarly, a load word will generate a misaligned if the address is not 4-byte aligned. So 0, 4, 8, 12 are all valid, but 1, 2, 3 or 4, 5, 6, 7 these are all invalid load word addresses. For all of those cases, if your final address, that is the base plus index, is a multiple of 4, only then you should proceed, else you should generate a misaligned exception. The same applies for store. Now there is also something called access exceptions, right? Access exceptions are something what we call as bus errors. Basically, you're trying to access some region of memory space which doesn't exist, right? You maybe have just 1 GB of RAM, but you're accessing address space which falls outside it, right? The other 3 GB space is, some peripherals exist, some other IO devices exist. You ended up accessing a region which does not map to any of these peripheral devices, right? So in such a case, you can get a bus error, which in the RISC V world is interpreted as an access exception. So a load access fault or a store access fault. You can also have some slaves where, it may also map to a legal slave. Maybe you're accessing a serial port, but the serial port generated an error during its computation. Right? That also is interpreted the same as an access exception. So assembly codes, this is a quick example of how you would write, arrays in C and operate on those arrays and the equivalent assembly codes here. This is a very straightforward. I'm going to skip this for now, but you can go through these slides, and if you have any questions, we can take that up in the afternoon during the doubt session. The U-type instructions. Now, there are 2 U-type instructions where you have 20-bit immediate fields. These are really large constants present within the instruction itself. You have 2 instructions called the LUI and the AUI PC. Now, LUI stands for load upper immediate. It's simple. It takes the 20-bit immediate and writes it to the upper 20 bits of RD. The lower bits are all zeros. Very simple, right? So this is an example. So you have LUI into X10. X10 is your RD register. You have 0x12345, which is your 20-bit immediate field. This will simply write the upper 20 bits of RD with 0x12345, and the lower bits will be all zeros. Right? Now, where is this instruction useful? If I wanted to load from a new 32-bit address, right? I will store the base address X10 with this particular value, and the lower 12 bits will come from the immediate field of the load. So I need only 2 instructions to actually perform the load operation. So memory address here will become 0x12345 plus the lower 12 bits which are present in the immediate field. So 6, 7, 8. Now, if you wanted to create a 32-bit constant, you can do the same with LUI. So let's say you wanted to create a constant 087654321. So you load the first 20 bits with 87654. Then you perform an add-I operation on the same register, but the 12 bits will tell you, the immediate field will tell you what the lower 12 bits are. Right? So that's how LUI is used to create very large constants, or 32-bit constants, 64-bit constants for RV64. This is how you can use it to do that. The AUI PC is very similar. What it does is it takes the current PC value, that's the program counter value of the AUI PC instruction that you're executing, and adds it to the immediate field. The immediate field is also created the same way. You take the bits, put it in the upper 20 bits, the lower 12 bits are all zeros. So this notion of adding zeros at the LSB side is known as padding zeros. Do not treat this as zero extension. See, a zero extension and sign extensions are always leftwards or always towards MSB. If you are adding something at the lower end, I would like to call it padding zeros, so that we have a very distinction between what is zero extension versus what is adding bits at the lower end. Now remember, your immediate fields are all signed extended. Right. So if I wanted to load dead beef, right, If I follow the same convention as before, I will take the 20 bits, 20 bits, it's going to be dead B, put it into X10, the upper 20 bits, and I add EEF. But you will not get dead B. What you'll get is dead A, EEF. Why? Remember, the sign bit of E is set to 1, which means the immediate of this is going to be FFFFFEF. Right? So when you add 1 to B, I mean, you're basically subtracting 1 because the upper bits, these are all signed operations in add-I also. So the B becomes A. So if you actually wanted to get a proper dead beef, what you would do is you would load dead C first, and then you would add EEF, so that the subtraction brings you back to the character B. Does this make sense? Any questions? Any confusions? Okay. Now we have branch instructions as well. So what's the time? 11:30, right? So we have a half an hour break. Okay, I'm just going to take 5 more minutes. We'll have a shorter break of 20 minutes so that we can cover more. We're going to talk about conditional branches quickly. Branches are basically instructions which will compare two operands. And if the comparison is successful, depending on the operation, you jump to a particular address, right? Now, where is this address? This address is present in the fields, the immediate fields. And these immediate fields are always multiple of 2, right? So you will not find immediate value 0 because the 0th bit is assumed to be 0. And the immediate fields will only capture the next 12 bits, right? So bit 13 is to 1 in some sense. So, sorry, bit 12 is to 1, yeah. So what you will end up with is an 8K addressing space, which is, again, this is signed indexing. So you can either jump forward 4 kilobytes or you can jump backwards 4 kilobytes, depending on the immediate field here. The different types of branches are very similar, very straightforward. You have equality. If RS1 is equal to RS2, then you take a branch. If it's not equal to, then you take a branch. Less than, greater than, less than unsigned, greater than, equal to unsigned. Now, can anyone tell me why the immediate field is 0? The 0th bit is 0. Why is it always that we are assuming that the immediate field is always going to be a multiple of 2?
That way we can jump to compressed instructions as well as other normal 32-bit instructions.
Yeah. So all instructions, whether they are compressed 16-bit or if you're a 32-bit instruction, they will always at least start at a 2-byte boundary. Right? If you have compressed, then there is a possibility that your instruction starts at a 2-byte boundary. If you don't have compressed, they're always going to start at a 4-byte boundary. Right? Therefore, there is no reason to have a byte addressable memory. It should always be a 2-byte addressable memory address. Right? So the 0th bit should always legally be always 0, because your addresses, your legal addresses can only be 0, 2, 4, 6, 8. It can only be even numbers, right? If I make the 0th bit as 1, that means I'm accessing an odd instruction, which is going to be illegal anyways. So in order to avoid that complexity of detecting all of that, you simply say that the immediate field is going to assume that the 0th bit is 0, which means the immediate field is scaled by a value of 2, and the remaining bits will tell you the other set of bits in the immediate field, right? So that's why we have a scaling factor of 2, because instructions can only start at a minimum boundary of 2. It can never start at an odd boundary. So more examples of assembly codes. I'm going to skip this. This is exercises for you. If you don't understand or if you have questions on this, we can come back and discuss them. Now, what we saw before were branches. These are conditional branches. Basically, depending on RS1 and RS2, if the condition successfully evaluates, Only then we jump, else we just fall through. Contrary to that, we have something called unconditional jumps. These are jumps which are always taken. There is no condition which depends on their execution. So there are two types of jumps. There is a JAL and a JALR. JL is very simple. You take the current PC value and you add it to the immediate field and you jump there. That's it. What you also do is the current PC plus 4 is written to the RD value, RD register, which is the PC of the next instruction after the JL, the one that follows it in program sequence. The address of that is written to RD, but the effective address of the jump is calculated by PC plus immediate. So this is the operation. RD is equal to PC plus 4, PC is equal to PC plus immediate. So this is where you will jump to. Now remember, you again have a 20-bit immediate field. And here also we assume that the 0th bit is 0, which means you can do a 2 MB jump. Either you can jump forward 1 megabyte or you can jump backward 1 megabyte from the current place. Similarly, you have a jump and link register. It's exactly the same as JLR, except that your base address is not PC, but it's from RS1. Right? So RS1 is added to this immediate field. That's your address to which you want to jump to. And RD still gets the value PC plus 4. So can anyone guess why do we store the next PC value in RD? What's the advantage of doing that? So in branches, we don't do any such storage, right? Branches don't have an RD field at all. They just compare and then they jump. There's no register update that happens because of a branch. But in case of jumps, we have an RD field, and this RD field is always filled with the next PC value. Why is that? Where is this useful?
We might need to come back to the place where we jumped after a subroutine call.
So functions, yeah. So functions will use this whenever you do a function call. You want to know where to go back to once the function exits, right? Once the function returns, you want to go back to the place where you had called it from so that you can execute from there. So that's why you would like to store the next addresses over there. So that's why you call these as returns and jumps, and these are more advanced interpretations. Okay. Finally, we have 3 important instructions: the eCall, the eBreak, and the fence instructions. eCall is an environmental call instruction. This is, I feel all 3, or at least eCall and eBreak, are more to do with privileged operations, but they've somehow been set up as the base ISA. So eCall allows you to go from one privilege mode to a higher privilege mode, right? So if you're in the user space and you want to get some work done, or you want to request permissions from the supervisor, you perform an eCall, right? So you will be able to go into the supervisor, and the supervisor will be now able to process your request, or further it can hand it over to machine by calling eCall again. So eCall allows you to go up the stack in your privilege mode. eBreak is like a breakpoint. You want to stop and debug at a particular point. If you have a debugger attached to your core, you can insert an eBreak instruction, at which point the control is transferred to the debugger or your host processor. And you can step through the code or check the register contents or memory contents or modify them as per your wish, and then execute back. A fence operation is a barrier sort of an instruction. So if you have multiple cores, or if you have a single core in some sense, you can ensure that the caches and the memory are now synchronized. So if you have dirty caches or write back caches, by executing a fence, you will make sure that the main memory has the updated values, so that other entities in your single core system or multi-core systems are now synchronized and they have visibility to the same contents. So sudo ops, apart from the 40 instructions, some specific combination of instructions, operands, and immediate values, we call them as sudo ops. Right? For example, if I wanted to perform a move operation, it's nothing but an add-I where the immediate field is 0. right? If I wanted to not a particular value, it's a XOR instruction with immediate value of -1 and so on, right? So you can do sign extend by simply adding by doing a add IW with this value 0. Okay, this is a 64-bit operation, by the way. Right, and similarly, lots of variants of the branches, right? If I want to do equal to 0, it's as good as putting RS2 as 0, x0 register, right? A few extensions to the I has got the ZICSR. You basically have instructions to check or access the control and status registers. And you have 6 instructions. They are called the CSR or the CSR operations. You can write, you can swap, you can set and clear bits of the CSRs using the integer registers as the operands over there. ifence is very similar to the fence instruction. It's just that fence only applies to the data memory. ifence also applies to the instruction memory. So what you do in an ifence is to make sure that you first clean the data memory, which means all the data caches, all the values, dirty values are written to memory. You clean out your instruction cache and then start fetching from scratch, right? So this is particularly useful when you're doing self-modifying code, where the updated code is still in your data cache and you want to fetch it from there, right? So what you do is you first fence the data cache, which means all dirty lines and all dirty instructions which are updated in the cache are now going back to memory. And you tell the instruction cache that you dump everything, you remove all the contents, and you start fetching it from scratch, right? So ifence is very useful when you're doing self-modifying codes. And finally, my last slide, what we looked at today is an RV32I subset. There are 4 more base instructions that you can choose from. If you want a 64I or a 128I, it's exactly the same instructions, except that the register sizes will become 64 or 128. There are a few additional operations. So if you're a 64-bit core, there are a few more instructions that you can do to perform 32-bit operations, right? And everything else is pretty much the same. Embedded, as I said, you only have access to 16 registers instead of 32. Right. So with this, I'm gonna stop for now, and we can take a break. We can start at 2.